We now will make the concept of a linear approximation a lot more precise, and then we can see how we can utilize these linear approximations. The good news is we have pretty much all we need in order to find these linear approximations. But let me just kind of remind you of something from the not so distant past. So let's say we have our function y equals f of x, and let me draw my x-axis, and let's say this is a, so this is my x value somewhere here, and then we know that the point that corresponds to the to x equals a, it would have ordered pair a comma f of a, right? We have the x value, and we have our nice explicit function, so we evaluate it, and that gives us the ordered pair. And if I draw the tangent line to this graph at this point, right? Yeah, so this is our tangent line. And the thing now is, when you talk about a line that's tangent to it just touches it at one point there. So you can see pretty much at that point there is no difference between the graph of y equals f of x and then the graph of my tangent line, which is in blue. And even when I am close to the point of tangency, so when I'm close to the ordered pair a f of a, again, there is very little difference between the y value on the curve and the y value on the line. They're not identical. So for instance, even right here, there's a difference, but it's not a huge difference. It only becomes relatively huge the further I go away from the point of tangency. So if I am interested in only values of x that are relatively close to a, right? So for values of x that are close to a, the tangent line serves as a reasonable, if not very good, approximation to the curve. So usually when we talk about approximations, you think, okay, I'm going to use one number to approximate another number. Like for instance, 3.14 is an approximation of the number pi, or 2.71 is an approximation of the number e, or 1.41 is an approximation of the square root of 2. But now what we're saying with this concept of a tangent line, we can approximate a function, a non-linear function, with a linear function, right? So let's just write that down. So for values of x, and I'll put this in quotes, close to x equals a, the tangent line, right, which is a linear function, so the tangent line serves as a, and I'll put this in quotes because this is somewhat subjective, a reasonable approximation, right, to y equals f of x, right? And that's why we use the phrase linear approximation. We're going to be using a line to approximate a curve. What line? Well, the tangent line. All right. So here's just some other notation that's a little bit different from what we've done. Now, let's think about it. So let's write down what we know about the equation of the tangent line. So we know that the slope of the tangent would be our derivative evaluated at a, right? Take our derivative, our function is nice and differentiable, evaluated at a, that gives us the slope of the tangent line, and then the equation of the tangent. So equation of tangent is, again, at this point, right? So this would be the point slope form, where it would be y minus the y value is equal to the slope times x minus your x value. right? And then if we want to write this in our slope-intercept form, then y is equal to, so add this to both sides, so bring over the f of a, it becomes f of a plus f prime of a times x minus a. So what we're now saying is this function f of x, for values of x that are close to a, can be approximated by this function, right? These are two functions, but this one is nonlinear. Or as we can see, definitely not a linear function here, whereas this one is linear, right? And we're going to call this tangent line the linear approximation. And to really emphasize that this is a linear function, we're going to give it a name. We're going to call it L of x, right? So let's write this down now. So if y equals f of x is differentiable, right? It has to be differentiable, otherwise that f prime of a is not going to exist, right? Not necessarily. So if y equals f of x is differentiable at x equals a, we define the, and it's sometimes called a local linear approximation. So I'll put that in, I'll put the word local in parentheses, but the local linear approximation to y equals f of x at x equals a, and this is how we define it. So we're going to use the letter L for linear, and it's going to be a function, but we have a nice formula for it. It's the same formula that's used to find our tangent line. So it's f of a plus f prime of a times the quantity x minus a. Right? And again, so let me state what I stated up there and say this. For x close to x equals a, our original function f of x can be approximated by this linear function. So I'll say this, f of x is approximately equal to L of x, right? And that's our linear approximation. Right? So the nice thing about it is we've done this process many times. It's just now we're giving it a different name, and we'll actually look at a couple examples right now of how we can use it. So after finding the tangent line, the question is, what else can we do with it, right? So here are a couple examples. All right, so first one, let's take a look at this function. Let's take a look at the function, which is definitely not a linear function. So it's x cubed times e to the x squared minus 1, right? Now, I'm not going to go through the trouble of graphing this function, but I think we can all agree that this is not a linear function, right? And let's find this linear approximation now to this function at the point x equals 1. So let's pick a convenient value of x. So let's answer this question. What is the linear approximation of f of x at x equals 1? All right. Well, let's go through the process of finding what we need. And we can actually, start using this formula and giving it a name that we've never really done before, right? So when you look at this formula, again, it's the two standard things that are needed. We need the function value at a. We need the derivative value at a. Use this nice linear formula, and that will give us our linear approximation. So let's first find f of 1. So f of 1 is 1 cubed times e to the 1 squared minus 1. Well, 1 cubed is 1. Then I'll have e to the 1 minus 1. So that's e to the 0, which is 1, right? So the tangent line and the graph will pass through the point 1, comma 1. But now the big thing is to find the slope. We have to make sure that our line has the right slope. If it doesn't have the right slope, then it's not going to be tangent, and it's not going to work as a linear approximation. Well, not in the way that we want it to work. So let's find our derivative. So f prime of x. So we need our product rule, and we're going to have our chain rule. So derivative of the first, 3x squared times the second, that's e to the x squared minus 1, and then plus the first, which is x cubed, times the derivative of the second, which is, we get back the exponential function, and then we have to multiply by the derivative of the inner function, so that's 2x, right? Well, let's see how this, it simplifies a little bit. We can factor out the e to the x squared minus 1, and then in parentheses I'll have a 3x squared there, and then x cubed times 2x, that's 2x to the 4th, right? So that's our derivative. Now let's find the slope of our tangent line. So f prime of 1. Well, if we plug 1 in here, it should work out pretty nicely. We'll have e to the 0 again. And then we'll have 3 plus 2. So we're going to end up with 5, right? So now that we have our function value and our derivative value both at the point of tangency, then we can write down what the linear approximation is. So this linear approximation is equal to, let me write it out symbolically, and then we'll plug our numbers in. So here's our formula. So our linear approximation is 1 plus 5 times the quantity x minus 1. So that's 1 plus 5x minus 5. So therefore, here's our linear function. It is 5x minus 4, right? And what this says is, so remember, so here is let me remind you, here's the original function. It's x cubed times e to the x squared minus 1. We've now found this linear approximation, which is a linear function. And then what the theory is that when x is close to 1, so for x close to 1, this function, x cubed e to the x squared minus 1, is approximately equal to 5x minus 4. But how could we even test this claim that I am making, that whenever I have an x value that's close to 1, this function value is going to be approximately equal to this function value? Well, we can test it out. Pick a number that's close to 1 to 1. So let's try x equals 1.01. That's pretty close to 1, right? Well, let's see what f of 1 is. So that's my original function. I'm going to plug this x value in and see what I get. So it's going to be 1.01 cubed, and then e to the 1.01 squared minus 1, right? And it turns out that evaluates to 1.051219577, and so on. Just keeps going, right? So that's the the function value, my original function, at this value of x. Okay, right. So whatever, this function really doesn't have, it's just an arbitrary function that I picked, and then here is its function value at a value of x that's close to this point of tangency. So now let's see what happens if I plug 1.01 into my linear approximation. So if I take L of 1.01, that's going to be 5 times 1.01 minus 4. And you see for this, for a linear function like this, to do the evaluation, I don't need a calculator. So for something like this, yeah, you'd have to use a calculator, right? For the most part, you'd have to use a calculator or some computing device. This, I don't need a calculator. All I have to do, because I can multiply by 5, this becomes 5.05, and then I can subtract 4. So look what I end up with, 1.05. So, accurate to 2 decimal places, these are identical, right? So that, in a nutshell, is what we mean by the fact that the tangent line, this linear approximation, it approximates the original function, right? And if I were to pick a value of x that's even closer, then I would have, again, even more agreement in terms of the number of decimal places that agree, right? So that's one example of how you can at least visualize, in a numerical sense, what we mean by a linear approximation. But here's another type of function, another type of problem that a linear approximation can help. Suppose we wanted to do this. Approximate the square root of 4.1 using a linear approximation. Right? Well, why would we want to do this when we can just punch this into our calculator? Well, pretend that we live in a world where there are no calculators. There, I said it, right? But yeah, suppose we didn't have a calculator, right? In fact, calculus, right, has been around a lot longer than calculators, right? So if you had to compute this, or at least approximate this with some level of certainty, and you didn't have a calculator, but you happen to know calculus, right? I think calculus trumps calculators any day. Well, we could use this linear approximation to do this. You might say, well, how am I going to do this? How am I going to use calculus and I don't have any function and I don't know any points, like how am I going to do a tangent line or anything like that? Well, the thing is, based on what you have to approximate, you would choose the appropriate function. You would choose f of x, and you would choose what point along that function you would want to find the tangent line, and it would have to be something that is close to 4.1, and you could compute the square root of that number quite easily, right? So there are a couple clues to the way these problems are set up that would enable you to make the right choice. Right? So let's walk through that process. Now, the function part tends to be the easiest, right? So since you're trying to approximate a square root, then we're going to use the square root function. So we're going to say, let f of x be the square root of x, right? And then I need to pick an a now. I have to pick an a that is close to this number, and it has to be an a that I can compute the square root perfectly. Well, in order to find the square root perfectly, then my number would have to be a perfect square. Well, can I think of a perfect square that is close to 4.1? Yeah, 4. So I'm going to let a be equal to 4. So what I'm going to do is find the linear approximation of my square root function at this point and then use that linear approximation to approximate the square root of 4.1, right? Okay, so let's go through it. So we need our f of 4. Well, again, we chose it because it was easy to find, or is easy to find. The square root of 4, that's 2. Now I need my derivative, right? So f prime of x, well, we know that this is x to the 1/2. So when we compute our derivative using our power rule, we get this. When we rewrite it, we get 1 over 2 root x, right? So then f prime of 4 is 1 over 2 root 4. So that's 1 over 2 times 2, so that's 1/4. All right, so that's 1/4. And then now let's write down our linear approximation. So the linear approximation of my square root of x at x equals 4 or a equals 4 is, so L of x is equal to, again, let me write it down symbolically, it's my function value plus the derivative value times x minus 4. Right? So what are we going to end up with? So we have our f of 4 is 2, f prime of 4 is 1/4, and then we end up with x minus 4. And in fact, I'm going to leave it like this. I'm going to say this is my linear approximation, and you're going to see why this is really helpful. So now my goal is to approximate the square root of 4.1. But remember, our principle is that our square root function is going to be approximately equal to this. So therefore, the square root of 4.1 is approximately my linear function evaluated at 4.1. So if I do that, so plug 4.1 into my linear function, and again, you can see this is why I don't need a calculator. Again, remember, we're living in a world void of calculators, but these are arithmetic operations that I can compute without using a calculator. So I'll have 2 plus 1/4 times the quantity 4.1 minus 4. Well, 4.1 minus 4, that's just 1/10. Right? So that's 0.1 or 1/10. I just prefer fractions. And then 1/4 times 1/10 is 1 over 40. So then, if I get a common denominator of 40, then I'll have 80 over 40 plus 1 over 40. So that's 81 over 40. That's pretty remarkable. Using this linear approximation, the square root of 4.1 is an irrational number, but I have found a pretty easy rational approximation. This 81 over 40 is a rational number, and it approximates this 4.1. Now, let's see if, so let's say now we're transported, suddenly we're back in a universe that has a calculator. So let's see what our calculator approximation is of 4.1. So from our calculator, right? So our calculator in its infinite wisdom says that the square root of 4.1 is 2.02484567, and of course we know it goes on. Again, because it's an irrational number, so it has a non-repeating, non-terminating decimal expansion. But then our 81, so here's our linear approximation, right? Our 81 over 40, or it's just 2 plus, 1 over 40, so that is 2.025. And that's not bad. I mean, come on now, it's not that bad. Look, if we round this to 3 decimal places, right? So basically, for significant digits, it's a really good approximation, right? So it shows you, it gives you a sense of how all of a sudden we can now start using tangent lines, right? And it makes you wonder, are tangent lines somehow related to how our calculator can do this? I mean, obviously the calculator is doing a little bit more because it can give us a few more digits, but maybe, maybe somewhere in the future you will learn of, not just linear approximations, but maybe quadratic approximations. Wouldn't that be interesting? Or cubic approximations. What if you could approximate a function using any degree polynomial? Well, in Calc 2, right, your second semester of calculus, you will likely learn about that. But for now, we're going to work with just linear approximations. So hopefully you found those two examples interesting, and just the concept now of using the tangent line for a little bit more than just finding a line, but you can see some practical significance of it. All right, see you in the next video.